So next on the agenda, we have someone from SGI and someone from Intel. However, the person from Intel is so popular, he's at the OFED workshop. I'll provide his introduction, even though he won't be here because, you know, that's just the kind of guy I am. Amir Shehata is based in Vancouver, Canada, and has been working on the Lustre project for 3 years, specializing in LNet. Prior to working on the Muls-Rail project, he was a primary engineer for the dynamic LNet configuration feature in Lustre 2.7. Now, the person who's doing, you know, who actually showed up is Olaf Weber from SGI. He joined SGI in 1998 to work in support, switched to engineering in 2005, and is now a senior software engineer working in Storage Software Group. Let's give a big hand to Olaf Weber for taking this on and showing up and being less popular than Amir Shehata. No. Olaf.
Okay, so I'm here to talk about Muls-Rail LNet for Lustre. You may have heard the project mentioned a few times already, and it might be a good idea to actually tell you what it is also supposed to be all about. So first, the what and why of Muls-Rail. Muls-Rail has been a long-standing wish list item, it's been known always under a number of different names: Muls-Rail, interface bonding, channel bonding. And there are some technical differences implied by these various names. And this particular project is a collaboration between SGI and Intel. Our goal is to land Muls-Rail support in Lustre. And mostly I'm going to be talking about exactly what it is that we want to do, as opposed to trying to contrast it with the various approaches that we could have taken but are not taking. So for our purpose, what is Muls-Rail? Muls-Rail is allowing nodes to communicate with each other across multiple interfaces at the same time. And those, in particular, a pair of nodes. So the multiple interfaces can be connected to a single network. But what we also want to make possible is that we can use multiple interfaces that are connected to different networks. And as noted, they must be usable simultaneously. So why Muls-Rail? At the SGI end, particular interest is big client nodes. For example, an SGI UV300 system can have up to 32 sockets in it. It's a non-uniform memory access system, architecture system. An SGI UV3000 can even have up to 256 sockets, also non-uniform memory architecture. Basically, a big system like that is, as it were, itself a kind of cluster. Much of the terminology that you encounter when discussing NUMA systems is therefore similar to cluster technology. So we talk about nodes, about interconnects, etc. And so a big client, effectively it is as if you are connecting a big cluster to your cluster. Except the interconnect in this case is the memory subsystem instead of InfiniBand or TCP, IP or Gemini or whatever. And as with any cluster-like system, a NUMA system has an internal topology, and there are big benefits to be had if the network interfaces that you use are close according to the internal topology of the system, close to the memory that the buffers you are using lives in. So from the SDI end, that's a big motivator for the Muls-Rail feature. Another one, this is the second example, increasing available bandwidth to Lustre server systems. Because in big systems, in big clusters, the bandwidth to the server nodes can become itself a bottleneck. Just adding a faster interface to the server, but not to the clients, does not help, because it's the slowest interface in the chain, ultimately, that determines how fast, what your latency, etc., for messages is going to be. So what we want is to add more interfaces to the servers. And today, you can do that, but when you do that, you end up having to redesign the LNet networks in the cluster. Because without Muls-Rail, each of those new interfaces now needs to be added to a separate LNet network. And then you need to distribute the clients across all those new LNet networks. And we want it to be simpler than that. So what the project that we're working on attempts to achieve is divided, as it were, in layers. First layer, basic Muls-Rail capability, where we multiplex across interfaces. This as opposed to striping messages across interfaces. What it means is a message goes out over a single interface instead of being cut into pieces and sent out over multiple interfaces at the same time. A side effect of that is that in order to actually use the multiple interfaces, you need to have on the server or on a big client more than one thread doing work. But both for the servers and for the big client systems that we are interested in, that should not be an issue. If you have a compute system with 32 sockets and only a single thread on that system is doing I/O, yeah, well, what can I say? So, second layer is to extend peer discovery to simplify configuration. Today, in the LNet code, if a peer connects, it gets automatically set up, unless you use something like the blacklist, whitelist feature that was discussed yesterday to be able to prevent that, for example. So we extend that mechanism to make sure that the interfaces of a remote peer can be automatically discovered and that we can automatically discover whether or not the remote peer is actually running a Muls-Rail capable version of the Lustre software. We want to enable configuration changes at runtime. That includes being able to add or remove interfaces on a node at runtime. Therefore, LNet control is used to configure the Muls-Rail feature in general, but also the networking setup in general. This as opposed to using kernel module parameters, because changing kernel module parameters means you need to completely stop Lustre, unload the kernel modules, modify the setup, reload the kernel modules, and, well, that's something we want to get away from. We do want it to be compatible with non-Muls-Rail nodes, so in order to use it, obviously the best way would be to have the big clients and the servers to be Muls-Rail aware, but it should not be necessary to upgrade the entire cluster in one go just because you're adding a single Muls-Rail node. And finally, what the feature provides is, now that you have multiple interfaces through which nodes can talk over the same LNet network, preferably, you can use that also as a way to add resiliency. In case one of messages over one of the interfaces aren't arriving, you can start resending them over another interface. And as long as you don't hit the Lustre internal timeouts, you can do a couple of retries and, well, maybe still get across without forcing a complete reconnect. So, to illustrate a couple of those ideas, this is a picture where you have a single fabric with one LNet network. The boundaries of the fabric switch-ins are shown with the dotted line. So all the nodes are connected. The big node, the, well, cluster in a rack, as it were, that is the UV. It also has a single leg into the fabric. So let's give it more legs. This is more or less how you can do it today. Single fabric, there are multiple LNet networks. On the client nodes that connect with a single leg into the fabric, you use a bunch of aliases to, well, somehow make it work, to make an interface visible on multiple LNet networks. At the UV end, I've given the UV 4 interfaces, each one connect to a single LNet network, and each of the OSSs is now also assigned to a single LNet network. So load is being balanced, but this is a rather complicated thing to have to set up, and it is in particular a rather complicated thing to have to do to an already existing cluster. So what we want to be able to do is the same fabric, but the configuration effectively should look like this. Single LNet, and the UV just connects all its 4 interfaces to that single LNet. Going further, you can then also start thinking in terms of configurations where you have multiple fabrics. So this shown with 2 different colors. The UV has legs on both fabrics. The lower client has a leg on the lower fabric. And in this case, the server nodes are all connected also to both fabrics. And in this kind of situation, the client nodes, the small clients, have still their normal bandwidth. The UV has 4 times that bandwidth because all 4 interfaces can be active at the same time. So that gets to the second part of the talk. How would you configure this kind of thing? After all, given that simplification of the configuration is one of the issues that we are trying to achieve. And then there are a couple of use cases that you have to bear in mind. So maybe you've just added interfaces to improve performance. Maybe you've done it to improve resiliency. Maybe just to get better usage out of large clients. And as noted, the Muls-Rail code is NUMA aware. Another example is that you may need some finer-grained control of traffic than the default rules would get you. And there's also, it is an example that Amir originally provided to me, what he called simplifying multi-network file system access. And I'll now go through a couple of these. But first, the configuration methods, then, there are twofold. First of all, there's the static manual configuration with LNet control. And when you do that, the following items always must be configured statically. The local network interfaces and how they are mapped to LNet networks, and what we've called selection rules, if any, which allow you to specify preferences among which interface to use, which network to use, which peer interface to use. If you do not define any of those rules, the default is always what we call a weighted round robin. That's basically we go from interface to interface, but we do keep an eye on the available credits on each interface so that an interface that is heavily loaded will not see continuous use while another one remains idle. The thing that may be configured manually, statically, but can be configured, can be discovered dynamically, are the peer network interfaces. So there is something, dynamic peer discovery, that you can enable to have the LNet configured peers automatically. So the basic concepts for static configuration is, on a node, you configure the local network interfaces, basically as today. If you want to, you can still do it with kernel module parameters. It's not really going to be advisable, perhaps, in the future, but it can be done. Existing configuration should continue to work. And you can configure then the remote network interfaces, basically the set of NITs that all belong to the same peer. The first one, the primary NIT of a peer, then second NIT, etc., etc. And configure the selection rules. So dynamic configuration, there the basic idea is that you still configure the local network interfaces, you still configure selection rules, if any, but peers are now discovered as messages are being sent or received. Basically, you want to send a message to a peer, or a message comes in from a peer, then the node sends an LNet ping, because then the ping reply gets you the list of interfaces of that peer, plus a field with feature bits, and we use one of those bits to indicate whether or not the peer supports the Muls-Rail software. And if it does, then we can push our own list of interfaces to that peer, so that we now completely know of each other which interfaces there are and which we therefore can use. The selection rules, they basically work by adding priorities. Higher priority is preferred, and the rules are basically pattern rules. And you can select priorities, say, for a network. Use, say, the first InfiniBand network, prefer that over a second InfiniBand network or over a TCP network. You can specify priorities for local NITs, local interfaces, which means that, say, the first InfiniBand interface is preferred over the second one. You can specify that a node should be talking preferably to a particular peer interface. And you can specify that there are local remote interface pairs, basically a point-to-point route that is to be preferred over other possibilities. So, simple example, a network setup where you want to have some improved performance. In this case, the OSS node has two interfaces, and using the syntax that is currently supported by LNet control for its configuration files, you see we define network type is an InfiniBand network, and the local NI's list gives the two interfaces, IB0, IB1. This is an example where it's more about improved resiliency. So there are, in this case, two networks, but we only want to fill over to the second network if the first one has, for some reason, some issue. Or what you could also have in a configuration like this is that, for example, your first network is fully connected, the second network is partially connected, but the second network might be preferable for bulk data. First network is low latency, the second network is high throughput. So the kind of configuration that you would see is on the clients and the OSS nodes. Again, you define network types, the first and second InfiniBand networks, and now you add a selection rule. So, for example, the first network, O2IB, gets priority 0. The second network, O2IB1, gets priority 1. And 0 is highest priority, 1 is lower priority, etc. This is another example where you have, in this case, an O2IB network and a TCP0 network, and you want to configure the nodes to be able to reach each other. And this is an example where static configuration, manual configuration, might make a difference, because instead of having the MGS, MDT, etc., specify all the possible failover nodes, what you now can do is you just specify the primary NIDs, provided you have a configuration where the peers are explicitly declared, because now, given the primary NID, even if it doesn't directly connect, you can use it to find NIDs of that same peer to which you are connected. So the kind of rules that you see, the kind of configuration that you now see is, again, network type for the InfiniBand clients, for the TCP clients on the right, rules defining the peers by primary NID and additional NIDs. So the primary NIDs are all InfiniBand NIDs, the additional NIDs are TCP NIDs. And then a selection rule on the InfiniBand clients where you say, okay, prefer all the InfiniBand NIDs, and on the TCP clients, prefer all the TCP NIDs, so that when they try to actually send any traffic, the TCP clients will just go straight for the TCP NIDs and not even attempt the InfiniBand NIDs to which they are not directly connected. Finally, here's an example think of as fine-grained traffic control. This is where point-to-point routes come into play. In this case, we have a single fabric, simplified with 2 clients, and let's say the top half is fully connected, the bottom half is fully connected, maybe just 2 switches. In between, there is, say, some inter-switch links. So there is a way to talk between the switches, between the 2 halves of this network. It's slow. You would prefer for those links to not be active. So given the list of clients and servers as given on the right-hand side, you end up adding a selection rule like this to make sure that client 1 will prefer using the top half of the network to talk with any of the server nodes. Since the client 1 is connected also to the bottom half interfaces, if it cannot reach servers over the top half for some reason, then it will still fall back on the red path. But it now becomes something that's just there for resiliency, rather than something that, depending on the vagaries of a simple round robin, would have been chosen whenever. So a bit about the project status. There is a public wiki page for the project on the lustre.org wiki. Code development is being done on a separate branch in the Lustre master repo. The patches for static configuration and basic functionality are currently under review and testing. Patches for the selection rules and for dynamic peer discovery are under development. Estimated completion time end of this year. Master landing date to be determined. although Intel has suggested that they would really like to see it in 2.10. Then there is, of course, a legal notices and disclaimers, and an opportunity for questions.
All right, I'm juggling now. Hey, Sarp, how's it going? I got one of these. It's just for you. Thanks.
Any questions? All right, Olaf, thanks so much. Give him a hand.